from our own Professor Keith Baker, who's a physicist. He's going to tell us something about the Higgs boson today. But first, before we do that, how many of you are going? The students here are thinking about going to college, right? How many of you think your parents can afford to send you to Yale? Okay, so everyone that put their hands down, put them back up, because your parents can afford to send you to Yale, right? Now the parents are going, now what the hell is he talking about, right? There's no way I can afford to send my kids to Yale. Actually, you can. Yale's got a very fantastic financial aid sort of program. We have approaching 20% of the student body are now first generation to attend college. Right? So there's been a big push to make certain that we have all sorts of diversity, including socioeconomic diversity. And I don't remember all the numbers, but the most recent ones I was familiar with, if your total family income, right, is under $150,000 a year, and that's most families in the United States, right? Yale guarantees that you will spend no more than 10% of that to send your kid to Yale. And you're thinking, 15,000, well, that's more than the tuition at UConn, which is 12. Well, that's right, but that's total. That's tuition and room and board. You can't send your kids many places where the room and board is actually less than 15,000. So it's actually cheaper to send your kids to Yale than to have them stay home, right? So boot them out the door, right? Right, and send them here, okay? All right, so Keith, otherwise known as OK Baker, is a particle physicist. I'm a chemist, and I actually gave Keith a piece of equipment not so many years ago, right? I don't think he's going to talk about that today, but you know, we all work together. He got his bachelor's degree at MIT in physics, I believe, right? Then he did his PhD at Stanford, right? Went on, went to Los Alamos National Labs in New Mexico as a postdoc, and then he became a faculty member at Hampton University. I'm not sure where that is, Virginia. But we were lucky enough to then attract him to Yale, where he came here in 2006. Yep, 2006, and at the time was the director of Wright Nuclear Structure Lab. And so he's been here working at the frontiers of particle physics for quite some time, and he's got a really interesting story to tell you. So join me in welcoming Keith.
Okay, so I'll try to also speak up as I get going. So let me first of all thank Professor Zim for giving me this opportunity to speak to you. It's a pleasure, it's an honor to be here to speak to you today. So as he said, I have been at Yale for just over 12 years now, and also I wanted to point out to you that I've been doing this science, this physics. This has been my passion since I was your age, 11 or 12 years old. This is all I've ever wanted to do, and I have finally a chance to do it. And I wanted to tell you not about all of particle physics, not even about all that I have done, but just to give you a flavor for what I think are some of the highlights of the things that I've done over all these years, just some of the highlights. So I wanted to talk to you about the Higgs boson, the dark universe, and what comes next. So this is our universe as we know it. Let me start this out. I hope that this works. Let's see if I make this work here. Yeah. So this is the universe's, so it doesn't come up here, I guess. All right. Doesn't matter, we'll skip it. Sorry about that. So this is our universe as we know it. It's filled with stars, with galaxies, with clusters of galaxies. It's filled with interstellar gas. It's filled with planets. And there may be, there's evidence really confirmed recently that there are black holes in space. All of this is what we see. And this is a Hubble Space Telescope image of all these clusters of galaxies and stars. So as a particle physicist, as a scientist, the same as Professor Zelm, I ask myself, we ask ourselves, what is the world made of? What's the universe made of? What holds the world together? Where did we come from? This is what scientists have been doing for many millennia, going all the way back to the start of civilization, maybe with Aristotle and others. So this is what we're doing. So after all of these years, we finally have an explanation of our universe as we know it. So here we are. This is us. So this is what we call the classical regime, where you have living beings like us. And we're made, and then of course computer chips, our hair, all of this. So we know that we're made of cells. These are made of molecules. The molecules are made of atoms. The atoms are made of an atomic nucleus surrounded by all of these electrons, depending on the type of atom that it is. And then this atomic nucleus is made of nucleons, protons and neutrons. So everything around us, the chairs, the seats that you're sitting in, the clothes that you wear, you yourself, this is what we're made of. And we can do more than that. We know how to trace time going all the way back to when the universe was just came into existence with this Big Bang. It wasn't an explosion, it was more a rapid expansion of time and space. But these elementary particles then gave way to atoms that then formed stars, and these stars are what made the heavy elements, the carbon that is and other heavy elements that form our Earth. Then we have these planetary systems that emerge from there, and then it goes on from there. We know that. We can now tell you what happens going back all the way 14.7 billion years ago in regions of space that are many, many light years from where we are now. We also have a model, a theory of how all of this works. It's called the Standard Model of Particle Physics. So over the last 100 years or so, a combination of quantum mechanics and Einstein's theory of special relativity, these were brought together and to make up this standard model, confirmed with all of our accelerators, all of our experiments about these new particles. And they led to this standard model of particle physics. So we know now that these molecules that are made of atoms, the atoms are made of nuclei, of a nucleus and electrons. And then these nuclei are made of quarks and gluons. So we know that now from all of these experiments that we've done. We know that there are 6 flavors of quarks: up, down, charm, strange, top, and bottom. We know that there are these leptons. We call them leptons. They're electrons and positrons, mu plus and mu minus, tau plus and tau minus. There are also neutral leptons, neutrinos, electron, muon, and tau neutrinos. We know that there are 4 fundamental forces. We know that there's the electromagnetic force. We know there's the strong nuclear force. There's the weak nuclear force, and there's the gravitational interaction. We know now that what gives rise to the weak force are these W and Z bosons. We know what gives rise to the electromagnetic interaction is light, photons. We know what gives rise, what mediates the strong interaction. And these are the gluons inside of these nucleons. So this standard model that we have is not just that a model was devised to fit the data. In some cases, even predictions were made and found to be true. The standard model of particle physics is called the most successful theory ever developed. With the standard model, again, we can understand our universe over energy scales that are just fantastic, many, many factors of 10, over distance scales that include clusters of galaxies all the way down to elementary particles inside of a nucleus. It's the crowning achievement of 20th century science. And the standard model has been tested thousands of times, lots and lots of different experiments, and it's always shown to be successful. There are other theories, and again, in particle physics, we call this the most successful theory ever developed, and we can debate that if you like. However, there's a problem with the standard model. In order for the standard model to work so well, all of the particles in it have to be massless. They cannot contain any mass. if they contain mass, then the standard model didn't work. So the last thing that had to be done with this wonderful, successful theory is to figure out, how do particles get their mass? How do elementary particles get their mass? We know that they do. We know we have mass and we're made of these elementary particles. We know that the clothes we wear, the chairs we sit in, the cars we drive, the buses we take here, all of that. So they have, all of this has mass. Where did the elementary particles get their mass? So let's start then at the top. We're made of these cells, cells made of DNA, molecules, and then there are these atoms. We know that most of the mass of the molecule comes from the atom. We know now where the mass of the nucleus comes from. These atoms are made of electrons and nuclei. The nuclei are what carry most of the mass of the atom. Now, when you have these nucleons, these protons and neutrons that are separated, they have a certain mass. This nucleus has a different mass. You bring all of those protons and neutrons together, they'll have a different mass. Why is that? It's because when these are brought together, they have a binding energy. It's the binding energy of the nuclei that makes it have its mass that it does. It's the binding energy between these nucleons, the protons and neutrons. That's what gives rise to the mass. So for example, if you have protons and neutrons in a carbon atom, 6 protons, 6 neutrons surrounded by these electrons, this is how the carbon atom, the basic constituent of life here on this planet, gets its mass. It's the binding energy. Now, what about what the nucleus is made of? The nucleus is not a fundamental particle. It's made of protons and neutrons. How do they get their mass? Well, the protons and neutrons are made up of quarks. So let's just take as an example the proton. The proton is made of 2 up quarks and 1 down quark in the constituent quark model. And there's other stuff going on in here, and I'll come to that just in a second. Now, these quarks, these up quarks and down quarks, they exchange gluons. This is how the strong force works. The mediator of the strong force are these gluons. And this is where the proton gets its mass from. It gets it from these gluons and their interactions with these quarks, okay? So there can be lots of quark-antiquark pairs, what's shown here, and they're connected by, and they interact with other constituents inside of a proton or inside of a neutron with these gluons. This is where the majority of the mass of a nucleon comes from. But now look, now all of our experiments tell us that these quarks are fundamental. They're elementary. They're not made of anything else. They're called fundamental particles. The same with the electrons and muons and tau leptons. They're not made of anything else. They are just a fundamental particle that are indivisible. So the question is, how do they get their mass? They don't have this binding energy that we talk about to give mass to the nucleus and to the nucleons. So this was the last piece of this standard model. In order for it to work as well as it did, we had to understand what mechanism gave rise to these fundamental particles like quarks and leptons. What gives them mass? So this is the story. So it's not just that they have mass. Why is it that there's such a difference in mass? Why is it that the up and down quarks have masses that, and we talk about mass in terms of energy units. It's a few MeV, up to like 10 MeV. Whereas the heaviest particle that we know of is the top quark. Why is its mass so large? It has a mass of 175 GeV, 100,000 times that or more of some of these quarks here. So this was the thing that, as Kurt said when I got here, this is what got me up in the morning, among other things, was to try to find out what was this, if this was the right mechanism, what was the mechanism that gave these fundamental particles their mass. There were competing ideas. Let me just say there were competing ideas having to do with extra dimensions or with supersymmetry. This was just one of several hypotheses about how particles get their mass. So this one is called the Higgs mechanism, named after Peter Higgs and Francois Englert. The mass mystery we felt could be solved by the Higgs mechanism, which predicted the existence of a new elementary particle, never before seen, a fundamental scalar particle. Some people called it the God particle. Some called it the Higgs particle, and that's what we'll go with. So we call this the Higgs mechanism. So the Higgs have been searched for decades. Lots and lots of people from around the world at all kinds of accelerators and all kinds of experiments had looked for it and couldn't find it. We collectively looked in different regions of space, phase space, mass versus coupling, and no one ever saw it. So finally, we knew how it coupled to mass if it really existed, but we didn't know its mass. We didn't know how heavy it was. So that was why we had to build this Large Hadron Collider in Geneva, Switzerland. So the first thing so this new discovery required these really gigantic detectors, these gigantic instruments that record the resulting particles as they stream out of these collisions. We'd also had to have a large accelerator. The largest accelerator in the world, the most energetic accelerator in the world is the Large Hadron Collider at this point. It's a powerful machine that accelerates these particles, and in this case protons, to extremely high energies and brings them into collisions with other particles. We also had to have really fast computers, and we had to have more than that. We not only had to have fast and powerful computers, but we also had to be able to make all of these computers work together. We had to be able to get all the data and distribute it to all of these people all around the world who were working at the LHC, 7,000 of us, more or less. And this was something else that so not only did we have to build the accelerator and the detectors, we also had to have computing to collect, store, distribute, and analyze the vast amounts of data produced by these detectors. And the technology was just wonderful. But let me also say, in my opinion, as impressive as the technology is, the best part of working on this is working with the people involved. It took some really dedicated people who were willing to work together collaboratively. Just the collaboration that I worked in, the Atlas collaboration, had over 3,000 scientists and engineers from almost 36 countries, speaking different languages, different politics. During the time that I worked at the LHC now, since it's been over 20 years, we've even gone to war with some of these countries, and I'm going over there, and we still found a way to work together. There, things said. So working with the people has been the most exciting, the best part of being in this collaboration. Let me also say, especially for the young people here, the worst part of being in the collaboration is working with all these people as well, okay? It cuts both ways. Everybody thinks they're the smartest person on the planet. Okay, fine. All right, I want to see if this works because it shows how the LHC, it may not work. Okay. Sorry about that. I went over these slides with my wife, and she said, still pictures is just going to put everybody to sleep. So I had some motion pictures to show you, but okay, it's not working. So here we go. All right. So we collide these particles, and the protons come in from this side and this side of this Atlas detector here, and they collide right here in the center. And just to give you a sense of scale, this is the size of an average person here compared to this big device that was built by all of these scientists worldwide. And I won't go through all of these details. What's important I want to bring out are two things. One, it's about almost 50 meters long, about 12 meters in radius. It weighs about 7,000 tons. And what I'm told is that even if the way it's built, that if you were to drop it in the middle of the Atlantic, it would still float, at least for a while anyway. The other thing I want to point out is this inner detector. The very first thing that happens when these particles collide is you start to detect the debris. And that debris is right here in this, the initial formation of this debris is right here in the inner detector. And this is one of the things that I did. This took 10 years out of my life, building these, what's called the transition radiation tracker. And when I say me, it was a group of really dedicated, fabulous people that I worked with, and this thing was finally built. Okay, so now what happens? all of that debris that comes out of these collisions, we have to sift through what is important, what is exciting, and what's not. Then we start to collect the data, which is shown here coming in. This is a time-lapse slide that shows how the data is collected over many, many months. And so what you see here in red is the background. We knew that this background existed, and we see the data fits it. But then there was this thing right here, this little peak here, right at 125 GeV, that had never been seen before. This was the Higgs boson. This was this new boson that looks a lot like the Higgs, and it probably is. So that's where we are. So after I started working on this when I was in my early 30s, and we finally found this when I came here to Yale, and it's just a wonderful feeling. I have to tell you, there were 7,000 people who were part of this new discovery. Everyone worked hard. There were people who worked on this much longer than I did. There were people doing this for even more than the 20 years that I've worked on this. But being a part of a new discovery, being a part of this thing that completes the most successful theory ever developed, it's just a wonderful feeling, okay? And it's just wonderful. Even now, I still just, I will tell my grandchildren about this, and I'll embellish the story to make myself look more important than I was, okay? So, now we know how elementary particles get their mass, and this is how it's done. And I'll start by giving an analogy. So, what would happen if Lady Gaga or Gosling were to walk into this room? I think it's Gosling. You would want to shake their hand. You'd want to get their autograph. You would want to interact with them somehow. And if they were coming in here to try to get a seat, they would have a harder time. They would have to go through all of you wanting to interact with them to get to their seat. Whereas if I walked into this room, nobody cares. I just walk right to my seat and everything is fine. This is the analogy with the Higgs mechanism. So we now know that there's this Higgs field. It permeates all of space. It's an invisible energy field that's everywhere in the universe. And the particles that pass through it, some particles like the photon, pass right through it. They don't interact with this Higgs field. They don't interact with it at all. So they can travel at the speed of light, and they have no mass. This photon is a massless particle. There are other particles like these light quarks or the electrons or muons. They interact with it somewhat feebly. They have sort of feeble interactions. So what happens then is they gain a small mass, and they have to travel at a speed less than the speed of light because they have mass. And then we have the heavier particles like the Z boson, the W boson, the Higgs, or the top quark. The top quark is the heaviest particle we know of. It interacts really, really strongly with this Higgs field, and that's why its mass is so large, because it interacts heavily with this Higgs field. And it has a velocity that's much less than the speed of light for a given energy. So that's the way the Higgs mechanism works. This is the way elementary particles get their mass. And of course, Peter Higgs and Francois Englert won the Nobel Prize for this. And the closest I came to winning a Nobel Prize is the Atlas and CMS experiments were mentioned, and that's perfectly fine. So now, here's the standard model of particle physics. The standard model we now know has 36 quarks. There are these 6 flavors of quarks I showed you. Each of them has 3 colors and 2 charges. We know also that there are 8 of these gluons that mediate this strong force. We know that there are 6 charged leptons, muons, electron and positron, and taus. We know that there are 3 neutral leptons, these neutrinos, electron, muon, and tau neutrinos. We know about the force carriers. We know that there's 1 neutral Z boson, 2 charged bosons, W plus and W minus, and the photon. And now finally, we know that this Higgs boson exists. This is a scalar particle, the first of its kind ever seen. So there are 58 known elementary particles in the standard model. But, however, there are lots of reasons to believe that this isn't the final answer. Some people ask me, how can you say this is the greatest theory ever developed, or the greatest model, if it doesn't include gravity? And the answer is, as my theory colleagues will tell you, blaming the standard model for not describing gravity is like blaming your toaster oven for not giving you orange juice. That's not what it was designed to do. The standard model was designed to explain the strong electromagnetic and weak interactions. And it does it wonderfully, brilliantly. But our universe is a little more complicated than that. There's more than just these particles that I've shown you. In fact, this is what our universe looks like. All of these stars and galaxies, all of these interstellar gas, all of these planets, all of this is just this tiny sliver of the total mass and energy budget in the universe. All of the stars, all of this interstellar gas, the planets, all of this only accounts for about 4% of the universe. Most of the universe is made up of, we now know, we label it dark matter and dark energy. We don't know what they are. We don't know what this is. We don't even know if it has a particle physics solution. It may be a solution that's beyond us. But as a particle physicist, this is what I do to try to see if there's a particle physics solution to what is dark energy that makes up almost 3/4 of the total mass energy budget of the universe, and this dark matter. And then there are other questions. One of them is just sort of what happened to the antimatter? If the universe was, we know the universe began as this rapid expansion of time and space called the Big Bang. And if that's the case, there were particles made and there were antiparticles made. All of our experiments, all my experience, all the work I've ever done, and all the work that my colleagues have done have shown when you create a particle in your laboratory, you create a new particle, you also create an antiparticle to go with it. At the moment of the Big Bang, this had to have happened. And particles and antiparticles, when they meet, they annihilate each other and they just give energy. So why is it then that the entire universe isn't just filled with energy, with photons? If you look out into space, you see that's almost the case. There are many, many more photons of energy than there is matter. But there is matter. We exist. So somehow or another, something had to separate matter from antimatter so that all of this could happen. All of these are mysteries, and there are more. What is dark matter? What's dark energy? What happened to the antimatter? So the solution is probably what we call a dark sector. This is what we are now calling it, because for reasons that I will explain later. But we don't know what it is. We don't know what dark matter is. Just like there are force carriers between the particles in the standard model, there could be force carriers between these dark matter particles. And there could be something even more elaborate than that. We just don't know. So we're calling it a dark sector, and this is what we're doing now. So I wanted to just show you some of the evidence for it. All right, so one of them has to do with the way that these galaxies rotate. This is what's called, this is the speed at which this galaxy goes around, okay? So most of the mass of a galaxy that we can see anyway is right in the center. And as you start to go out to the edges, there's less and less of this luminous matter. As you can see, I say luminous because you can see it with your telescopes on Earth. So if you just look at the luminous matter, this is the way the speed should look as a function of the distance from the center of this galaxy. It should maybe rise like this, and then it should fall off. But it doesn't do that. It actually follows a different curve. It doesn't fall off. It continues to be at this healthy rate up here, very much higher than what's expected. What this suggests is that there's more matter inside of here than what you can see. All of this luminous matter is just a small part of the total matter that's in this galaxy. And you can see this in different kinds of galaxies, spiral and elliptical galaxies, for example. You see the same thing in all of them. There's more matter inside of here than can be accounted for with all of this luminous matter, stars and galaxies and quasars and all of that. Another example has to do with gravitational lensing. So if we look at distant stars, the light that comes from these distant stars that come to us on Earth and hits our detectors has certain features to it. and that is it has these rings around it. So just like if I were to put photons, send them through a lens, these photons can be bent, given a lens. You can focus them or you can make them diverge. When the light comes from these distant galaxies, they pass through this dark matter, and they too have this lensing effect. So for example, these rings that go around here, or the way that they show up in our telescopes, this is called gravitational lensing, and this is one of the reasons why we know that there has to be something else out there. And then the other one, this actually happened just a couple of years before I came here to Yale, the bullet cluster. So these are clusters of galaxies, and each of the galaxies has billions of stars. So these clusters of galaxies came together over many, many millennia, and they collided, and they passed through each other. So when these galaxies collided, we saw that all the particles that collided here, that's shown in red, this is the heat or the light that comes from these stars, these collisions. All of it was sort of kept right here in the center of this collision. Whereas we knew now, if you look at gravitational lensing, and there are other effects, that there's a lot more mass out here in blue, shown in blue here, than can be seen. There's a lot more of it, and we call it, again, dark matter. This was a smoking gun. This was another one of the smoking guns that says there has to be more going on here than just what we see in the standard model. So, and believe me, there's other evidence as well. So, whatever this dark matter and these dark matter carriers are, these dark forces or dark sector, we know that it's non-luminous. It doesn't give off light. We know that it has a very small, feeble interaction with us, with the standard model. The only evidence that we have of it is through the gravitational interaction, and that's the weakest of all the known forces. We know that just the standard model, just the 4% of the universe that we know, and we know extremely well, has 58 different kinds of particles in it. So it's naive to think that whatever this dark matter is, that it's just one component. There could be lots of different dark matter or dark sector particles with different components. And whatever it is, it dominates the matter budget of the universe. It's the predominant way that our universe was formed. So all of this, you don't have to know, this is just sort of the jargon we use. We can say that whatever these particles are, if it's a particle physics solution, they're either going to be vector or pseudoscalar or scalar, or they're going to be fermions. They're going to have half energy spin. That's what this is telling you. So so we find ways to look for all of these kind of particles that could be a dark matter particle. So I'll show you a couple of examples. One where it's to do with kinetic mixing with a photon or with a Z boson. So that was dark matter. Now there's dark energy. Dark energy is a mystery. The very best theories that we have, the standard model of particle physics, when we try to apply it to explain dark energy, we're off by over 100 orders of magnitude, 10 to the 120 to the power of 120. That says we have no idea what dark energy is. Dark energy, what it does is, at the time of the Big Bang, when you had all of this mass and energy in a small region of space, then it began to expand very rapidly. But all of the matter and energy is still enclosed in this region of space that is expanding. So that means that all of this matter is pulling back on it. As it expands, the gravitational interaction is saying you got to slow down, because that's what gravity is. It's an attractive force. So what this says then is that if this is the moment of the Big Bang and this is going into the future, we wondered, well, the universe is expanding, but because all this matter and energy that's enclosed inside the universe is pulling on it, it's going to expand to a certain point, but then it's going to start to come back in on itself. This was the Big Bang, and this is going to be called the Big Crunch. The universe is just going to come back in on itself and explode after many, many billions of years. Another possibility is, at the time of the Big Bang, as the universe was expanding, it's expanding at a rate that it's going to slow down, but it's going to continue to sort of have this size, the size of the universe. And it's just going to meander along forever. Another possibility is that after the Big Bang, the universe was expanding, and it's expanding at such a rate that it's still going to always expand, but at a much lower rate than right at the moment of the Big Bang. But we now know that none of those are true. When I was a junior faculty, just starting to teach my students, I told them this. I told them that, you know, these are the three possibilities of our universe. But I was wrong, completely wrong. We now know that not only is the universe expanding, but it's speeding up as it expands. It is an accelerated expansion of the universe. So the universe at some point is just going to become so huge and dark and cold that no life can exist in it. But it won't happen, you know, in your lifetime. It'll be billions of years from now. The other thing we know is that it's temporal. If the amount of dark energy that exists now existed at the moment of the Big Bang here, none of us would exist. So it's temporal. It changes with time. We have no idea what causes that. It could be something that we just haven't thought of, have no idea of yet. And all this is just data. I won't go through this. It just shows that the universe, for a critical density where the universe followed one of these scenarios, this data that's shown here would have to be somewhere down here. And if it was way up here, we could probably explain it with the standard model, but it's just barely here. It's just barely above this critical density. So we don't know how to explain this. This is what this is telling us. So that's dark energy. So what's the properties? Whatever dark energy is, it opposes gravity. It counteracts gravity. Gravity wants to pull all the matter in. Dark energy says no. We're not only going to counter it, but it's so much of dark energy that the universe isn't just expanding, it's speeding up, it's accelerating as it expands. It has a time dependence, it's temporal, it's ubiquitous, it's everywhere. It accounts for almost 3/4 of the mass energy budget of the universe. So, when I say that we have no idea what it is, that doesn't mean that we don't try, okay? So, there are two possibilities that people sort of seen. Albert Einstein claimed that there may have been, well, in his day, there was a claim that there was this cosmological constant. It's just a theory that says that in space, there's this constant of energy, and this is what's causing it. There's also this thing called the quintessence model, and this is what excites me because this says in the quintessence model that there are particles that give rise to this dark energy. And I'll give you a couple of examples of this. So let's talk about some experimental searches. And I'm just going to give you a few examples. There are many, many more. But these are examples of what I have worked on. So let's talk about this vector portal where there's this kinetic mixing versus the mass of whatever this particle is. Now, all the experiments that have been done up to now, all the experiments are what's shown in these colored regions here. So in these colored regions, what I show here, this is the coupling of whatever this dark matter particle or dark sector particle is. This is its coupling to standard model, to the standard model particle, versus here along this axis is the mass of that particle. And we give it in energy units and electron volts. So this is a log scale. So this goes from 10 to the minus, 17 all the way up to 10 to the plus 12 electron volts, tera-electron volts. So, and everything that's shown in white here has not been explored. This is a region of parameter space that has not been explored yet. We haven't come up with a clever enough experiment to do it, to probe whether this thing has a coupling in this range and whether it has a mass somewhere in this range or in this range. So, this is what it looks like sort of today. And this is one of the regions that had not been explored, and I wanted to do this when I was a part of the Higgs discovery. So let me set this up. What's different now? What would you do that's different? Well, let's take an example of Galileo. Galileo, after learning of this new tool, this telescope, Galileo was, so telescopes were originally invented so that you could see enemy ships coming to your city from distance, and you could prepare yourself to fight, okay, defend yourself. Galileo instead pointed his telescope at the moon, and he discovered mountains on the moons. He also discovered the telescope was used for the discovery of moons on Jupiter, that planets orbited the sun and not the Earth. Telescopes tell us that the sun has sunspots. The lesson here is, with new tools, there's opportunity. If you, in your lifetime, have some new discovery or some new technology, you should think about how can this be used to make some new discovery or maybe solve these problems. So this is what I worked on since I've been here and been a part of the Higgs discovery. The next thing was, can this Higgs sector, because this is unlike any other particle in the standard model, can it couple to this hidden sector or dark sector? This is the thing that I'm looking at. And also, all this is just jargon. It means this is the standard model stuff over here. The Higgs couples to all the standard model. We know how it does it. Does it couple to this dark sector? So this is how the experiment analysis was done. Let me just say this, okay. This is no time to be humble, okay, because I just spent too much time. So I'm going to tell you, I didn't come up with this theory, but I was the one who pioneered this analysis at the LHC. I was the one who said, okay, what if now we look in this channel where this Higgs decays to 4 leptons in the final state. But now, instead of this Higgs just coupling to standard model particles like the standard model Z boson, what if it couples to something that's beyond the standard model, a dark Z, a dark vector boson? So the collisions at the LHC, these are proton-proton collisions. At these high energies, it's mainly the gluons that are scattering. So this is called gluon-gluon fusion. So the gluons inside the proton are what are really colliding in these collisions. They give rise to the Higgs, which we've seen. And then I look for evidence for this dark Z. And in the interest of time, I probably won't go through just the details. This is just the strategy that I proposed, and it was fine. It was accepted. But since the end of 2012, after the Higgs was discovered until now, we've looked for it and we've seen nothing. There's no evidence for this. Where this dark Z would kinetically mix with this standard model Z, and we would look for some peak in that spectrum. That's what this is saying. We look for some peak in this off-shell distribution of the Z boson, this dilepton invariant mass distribution, and we see no evidence for it. I'll give you another example. Light shining through a wall. Okay, in this case, what happens if I have a laser shining photons? And these photons, okay, I don't know what I'm doing, but okay. I'm too close to that mic, okay. So just as neutrinos can morph from one type to another, what if these photons can morph into this dark sector particle? Let's just call it X. So you have a very powerful laser. You put this laser into, you point it at this wall here. And during the course of its travel from the laser to this wall, what if this thing were to kinetically mix or morph into a dark sector particle? Now, these things are feeble. They have very small interactions with the standard model. So these would go right through this wall, whereas photons themselves, if they did not kinetically mix with this dark sector particle, they would bounce off this wall. They can't go through the wall. So if it kinetically mixes with this dark sector particle, this can go through the wall, and then the same mechanism that made it mix over here would now make this mix back into a photon, a standard model photon that you would detect in your detector. So you'd have light coming over here, and if you saw light in your detector, you knew in a properly designed experiment, the only way this could happen is you had a process like this. This would happen in free space. You can also pass this through a magnet and look not just for vector particles, but this could be a scalar particle or a pseudoscalar particle. And that's what these light shining through wall experiments, when you have a magnet, can do. These would, via what's called the Primakov effect, they would convert into these dark sector scalar and pseudoscalar particles, pass through the wall, and then you put another magnet on the other side of the wall and make it convert back into a photon that you detect in your detector. So These were experiments that I started at the Jefferson Lab Free Electron Laser. This at the time was the most powerful source of photons in the world. And this was the experiment. We had a magnet here, we had a magnet here. This was the laser light coming in, and here was the wall that we had here. And here was our detector over here. And this is a photo of the setup. And we saw nothing. We saw nothing. The only thing that I can brag about here is that for the time, this was the most, the LIPS experiment, this was the most sensitive measurement in the world. We were the most sensitive of all. And then since then, we've been outdone by other groups in Switzerland, Germany, and at Fermilab. But it's fine. For a brief while, I was very happy about this. We saw nothing. You could also do the same thing by pointing your detector at the sun. There could be lots of these dark sector particles coming from the sun that maybe you can detect in this big magnet that's called the CERN Axion Solar Telescope, where you point this big cannon at the sun and you track it during the daytime. So this is on a device that allows it to rotate like so, and you can follow the sun as it goes across the sky. And look to see, do you see evidence for something that the only way it could get here is if it converts inside of this magnet and you detect it in your detector. So that was done. Still nothing. We saw nothing. And that's been going on now for many decades now. Actually, I think it's shutting down in the next couple of years. What about dark energy? Well, dark energy, again, we really don't have a clue. But there is this model I can test against. It's called the quintessence model of dark energy. So what is one example? An example of a quintessence particle is what's called a chameleon particle. And as the name implies, a chameleon particle is a particle that its mass depends on its environment. If it's an empty space, it has zero mass. But if it goes into some region of space where there's matter, then its mass changes, its mass grows. So you can use this, and what we did was to use this in the following way. Here's a magnet, here's a laser. You point this laser into your vacuum chamber, this is in vacuum, and in some cases, these photons can convert into this chameleon particle. They can connect with the magnetic field and make a chameleon particle. This chameleon now has a certain energy so that when it sees this vacuum window here and this vacuum window here, it can't go through them because it would have to have a mass bigger than the energy that it has. So it just bounces around in here. So you can leave this laser on for a few minutes or a few hours and try to fill this whole space with chameleon particles. Then you turn the laser off. So now there's no more light, laser light going through here. So after some minutes or hours, the only way you would see light here is if, in a properly designed experiment, is if one of these chameleons converted it back into a photon and you saw it. So that was another experiment we did, and we still see nothing. So here's how I want to conclude. I've talked to you about dark sector particles, dark matter, dark messengers. I've spoken to you about dark energy, the accelerated expansion of the universe. I've spoken to you about the different tools that we use, the LHC, the Atlas collaboration, these big detectors, and small tabletop experiments that I've done in the lab right here on campus and in other labs where you don't build a large Hadron Collider. You don't build that to do those experiments, but they still can give you a sensitivity that you can't even get at the LHC. But what I want to end it with is the thing that excites me the most. This is where the discovery is going to come from. 10 or 15 years from now, Professor Zelm is going to invite one of you young people that are in the audience right now. He's going to invite you to come back and tell us what dark matter really is, what dark energy really is. And you're going to stand up here in front of all your friends, your parents and grandparents, your children, if you have any by then, and you're going to tell us what it is. And nothing that I've said today will be in your talk. It'll be in something new. So that's my talk. That's it.
Keep those really optimistic that I'm going to be around here in 15 years.
Of course you are. Of course you are. You don't stop.
I hope so. I'm not so sure. I'm not so sure of that. Questions for Professor B? Gotta have some questions. Right over here.
So, can you, I don't know if you know this, or if it's known, but can you explain why some particles interact more with the Higgs field than others? Like photons don't interact at all, bosons interact with, but do you know why?
Yeah, so the question was, why do some particles interact more with the Higgs boson than others?
Yes, it is a property of the Higgs field itself. The way that it couples, the way that the Higgs field couples, the Higgs boson has very specific properties. We can tell you the coupling. Our standard model tells us that to a great precision, a precision of just a few percent. So what it says is that a particle like a photon should not couple at all, or gluon should not couple at all directly to the Higgs. That's a property of the field, and that's a property of the particles that pass through it. On the other hand, the top quark has to interact very heavily with it, and we know how to calculate that. It's not something that just falls out of the air. It is something that people have spent many decades prescribing this Higgs field, and that's just the way it works. Yeah. That's correct. The Higgs field and the particle that goes through it, right? So, I gave a talk. Let me just put this out here, because I gave a talk in my home state of Arkansas some years ago, and there was a young person like you who stood up and asked me, "Can you bottle the Higgs field? Can you bottle it?" And the answer is, I don't know, but no, I don't think so, because it's pervasive. It passes right through, it's everywhere. So if you could bottle it and somehow this energy field convert it into something that is useful. Okay, I wanted to get that out there before you asked me a question. I get embarrassed again, so I don't know. There are problems I don't know the answer. So I just followed up on your question just to get that out there. Okay. What was there before the Higgs?
Before the universe.
Oh, yeah, that's another good question. I don't know. I don't know. There are lots of ideas. Let me just say this to you. If you want to go into science, always make sure that you have data to support your ideas, okay? So data is always that brick wall of reality, right? There are ideas that there are just lots and lots of universes, what's called a multiverse. We just happen to live in the one of these many millions and billions of universes that supports life. Not all of them support life, at least not the life as we know it. That's one idea. Another idea is that there's a universe sort of within our universe, that we're coexisting with other particles. There could be a young woman just like you made of a different kind of particle that's sitting right in the same region of space that you are, but you don't interact with it, or you interact very feebly with it. All of these are ideas. We have no data to support them. So it's a really good question you ask, and I don't know. I don't know the answer. What existed before this universe? So, yeah.
Right here, the T-shirt. Yep.
So, when photons moving through that kind of cloud thing, it doesn't have any mass to just interact. But if, let's say, if you shrunk a person down to that size and we put them through the clouds, would they interact as more of a photon on the top of one?
So we're all made of, at its basic level, molecules that are made of atoms, that are made of protons and neutrons and electrons. And the particles inside of the nucleus, inside of the nucleons, the quarks, are mainly up and down quarks. not top quarks. We don't have top quarks in us. The top quark decays immediately when it's created. It decays immediately. So we would interact like up and down quarks. We would interact not very heavily like a top quark, but more than a photon, somewhere in between, because that's how we're made. We're made of these up and down quarks. And all the chair that you're sitting in, all the car that you drove, your home, that's what this world is made of. Yeah. Yeah. So some intermediate interaction strength. Yeah.
So like you were saying about bottling the Higgs boson field is almost impossible.
I should have kept my mouth shut.
I just wanted to ask, I've seen a lot about Higgs boson being an unstoppable force of energy with no stable environment here. It always creates this instability within itself. So I was keen to know that, is there any way we can harness this instability of the Higgs boson?
Right. Okay, so you hit on another really good point. You all asking really good questions. If the other part of the Higgs that has to happen is the Higgs has mass. It's 125 GeV. Therefore, the Higgs has to interact with itself. There has to be a Higgs-Higgs interaction. And we're looking for that. We're looking for that at the LHC. Until then, we actually don't know how it interacts with itself. We don't know exactly why its mass is what it is. Why is the mass 125 GeV? All of the theories sort of suggested that it should have had a higher mass than it does. Where it sits now at 125 GeV gives rise to some instability in the universe that we don't understand yet. But we will when we see and study this Higgs-Higgs interaction. The problem is that at the LHC, well, to see this Higgs-Higgs interaction, you need, this is more jargon, you need sort of thousands of inverse femtobarns, thousands, 3,000 inverse femtobarns to just see some evidence for the Higgs interacting with itself. Right now, we only have, even after running for almost 10 years, we still only have like 100 to 150 inverse femtobarns. So will we ever reach 3,000 inverse femtobarns with this machine? I just don't know. So it is a good question. We have to understand that. This is a big, big enterprise now at the LHC, but it's going to take many, many years before we get there, if we get there at all, because we're going to upgrade this Large Hadron Collider from the luminosity, the number of protons that collide. We're going to upgrade it, and we will run the upgraded LHC around 2026, 2027, and run it for 10 years, and we'll see. We'll see how close we can get to that. So until then, the questions you asked about the instability of the universe and the Higgs interaction has to wait. Yeah. Yes, sir.
So there's this sort of symmetry breaking. You have to have an antiparticle for every particle, so you never make one without the other in the lab. So in quantum mechanics, the molecules have energy levels. If I interact in the lab, I can take something and move it up and move it down. So I can never move it in one direction. I can't do that in the lab. So anytime I do that in the lab, I can't. But I know in the universe, I have spontaneous emission. I don't know why I have spontaneous emission, but to get a thermal equilibrium, I have to have it. So is that sort of symmetry breaking the same sort of thing you're talking about? Is it possible to have the same order?
So that's correct. So spontaneous symmetry breaking is this idea of spontaneous symmetry breaking that you described actually did not come out of particle physics. It came out of condensed matter physics and I guess in chemistry. And that is, if I have like a pencil that's, or a pen or a needle even, that's very thin, and I have it resting on this tabletop so that it's just sitting here, no interactions. It's very, very sensitive to, falling over one way or another. Just walking past it will do it. Now, That means that this needle is symmetric. It has a symmetry around it in all directions. It's not until that needle falls over that it chooses a direction in space. Now you have a symmetry breaking, and that's what we call spontaneous symmetry breaking. The Higgs mechanism was like that. The Higgs mechanism is a result of spontaneous symmetry breaking. It's called, I should have brought a plot to show this, where you have a Mexican hat potential. You can have a Higgs particle or some particle that's in there, and it's just, it's at the top of the Mexican hat, and it could fall anywhere inside of the ridge of the Mexican hat. Once it does fall, it chooses the direction, that breaks the symmetry, and that's spontaneous symmetry breaking. So the answer to your question is, I actually think you're in a better position, if I can just say it, Kurt, to answer that than I am, because it didn't grow out of particle physics, it grew out of your field. Okay, so that's the end. Yeah.